I have a pleasure to thank to all the organizers for creating such a fantastic atmosphere for all of us. So let's make a big applause. Yes, so today I will give a talk about random partitions, and since the background of the audience is very different, and also there are many young people, so I will start with classical results. So I will present some classical results about random matrices, and then I will switch to random partitions. I will explain what are the similarities between random matrices and random partitions. And I will present two different models of random partitions. And then I will show our main result, which shows that asymptotically these two models are governed by the same asymptotic. And finally, I will show some applications. So let me start with the first model. This is a continuous model. And it is coming from statistical mechanics. So this is called a one-dimensional Coulomb gas system, which is also known as beta ensembles. So this is a model of n particles. These particles are living on the real line. And their joint probability distribution is given by this formula. So here we have two parameters. So the first parameter is parameter beta. So beta is an inverse temperature, and this is a real number. And we have also this function v. So v is a potential, and this is a quite general model, but this model is strictly related with random matrices. So let's look at the very specific example. So when beta is equal to 2, and your potential is quadratic, it turns out that this model is strictly related with Gaussian unitary ensembles. So Gaussian unitary ensemble, this is one of the most classical model of random matrices. So what you want to do, you want to look at random Hermitian matrices of size n times n that are distributed with respect to the Gaussian measure. And what you want to do, you want to look at the eigenvalues of your random matrix. So you look at the eigenvalues. These eigenvalues are real, so they are given by some numbers L1, L2, and so on. And you want to ask all sort of questions about these eigenvalues. So a typical question is, what is the global shape of these eigenvalues when your random matrix is tending to an infinity? This is a very classical question, one of the very first theorem in random matrix theory. That was discovered by Wigner. So here on this picture, I sampled eigenvalues of some large Hermitian matrix, and you can see at this picture, I hope you can see it, that if you look how they are distributed, it looks like a semicircle. And this is one of the very first famous results that we have a law of large numbers. Namely, if you look how the eigenvalues of a very, very large random Hermitian matrix look like, they're starting to be closer and closer to this shape. And when n is tending to infinity, their distribution converges to this shape. So it was discovered by Wigner. And let me also tell you that when beta is equal to 1, you have another famous model of random matrices, which are so-called Gaussian orthogonal ensembles. They were also mentioned, I think, in the talk of Jonathan. When beta is equal to 4, you have Gaussian symplectic ensembles. So all of these three values of beta gives you some random matrix model. And finally, when beta is arbitrary and we have still the same potential, there is a famous matrix model of Edelman and Dumitriu of so-called Gaussian beta ensembles. And then what is interesting is that this limit shape, if you scale your eigenvalues appropriately using your parameter beta, the limit shape doesn't depend on beta. So there is this universality here that you always see this semicircle law, and it really doesn't depend on beta. And once you have this, you can also ask what is happening, what is the second order asymptotic? So what are the fluctuations around this limit shape? And for a large class of models, so for a fairly large class of these functions v and arbitrary beta, it was proven by Kurt Johansson that the fluctuations are Gaussian. So we have law law of large numbers, we have central limit theorem, and then you can start ask more questions. So this was a global asymptotic, but then you can also ask questions about something that is called edge asymptotic. So for instance, what is the second order asymptotic of the largest eigenvalue? So this question was one of the questions that was famously answered by Tracy and Whedon. So Tracy and Whedon found that if you look at the second order asymptotic of the largest eigenvalue, it is given by some new law that now we just call it Tracy and Whedon law. And they also knew that there is this law also for beta equal 1, beta equal 4. And then this result was generalized for Gaussian beta ensembles by Ramirez, Ryder, and Virac, who constructed Tracy-Whedon for arbitrary beta. And finally, it was generalized to, again, quite large class of potentials V by Burjat, Erdős, and Yau. So, okay, so these results that I showed you, for these results, what we do, we fix beta, and we take n to grow. So then you can ask other questions, because you have this other parameter beta. You can ask what is happening if your temperature is changing together with your model. So this is called high temperature regime because of this physical interpretation of beta as the inverse of temperature. So for instance, here, if gamma is equal to infinity, this corresponds to a fixed temperature beta. But you can ask some questions, what is happening in the regime when this gamma is some number? And these results are, these type of questions were posed more recently. So here I'm going to show you the law of large numbers and central limit theorem. So again, we have a large numbers, so there is some limiting shape. And now this limiting shape, of course, it depends on this parameter gamma. And because we know that we have a semicircle law for gamma equal to infinity, it turns out that this is some law which interpolates between the semicircle law and the normal law. And we also have central limit theorem for global asymptotics in this regime. So okay, so these are results about random matrices and log cases. But now let's change the topic and let's do something which looks a little bit more like combinatorics. So of course all of you probably know what is a Young diagram, what is a standard Young tableau. But let me just quickly recall that the standard Young tableau is a filling of a Young diagram by numbers from 1 to n, when n is the size of your Young diagram, such that the numbers are growing in columns and in rows. And we have this curious identity that if you sum over all shapes of a fixed size d, and then you look what is the number of standard Young tableau square, it turns out that this is equal to d factorial. So now we know a very nice combinatorial proof of this, which we also saw on this conference, which is RSK algorithm. But initially, this identity came from representation theory. So how to see this from representation theory? This tells you that if you take a regular representation of a finite group, you can always decompose it into irreducible representations. And then we know that the sum of the dimension square of all the irreducible representation gives you precisely the size of your finite group. And this identity is precisely applying this theorem to a representation theory of the symmetric group. So for the symmetric group, irreducible representations, they are naturally indexed by Young diagrams. And it turns out that the dimension of an associated irreducible representation is given precisely by the number of standard Young tableau. So once you have this, you can very naturally define a probability measure on the set of Young diagrams. So secretly, you are actually defining a probability measure on the set of irreducible representations of a symmetric group, which is called the Plancherel measure. So this construction actually works for arbitrary finite group. But in the case of the symmetric group, your random Young diagram is sampled proportionally to the number of standard Young tableau square. So in other terms, what you're trying to do, you're trying to ask some kind of questions. What is a typical random irreducible component if I decompose regular representation of the symmetric group. And we also saw this formula. So there is a beautiful, beautiful product formula for the number of standard Young tableaux given by Frame, Robinson, and Trell. So in particular, the Plancherel measure that I just mentioned has also this very, very nice product formula. So this is a very nice and also very natural probability measure on the set of Young diagrams, which is really coming from representation theory. And you can just start asking all sort of interesting questions about asymptotics. So that's exactly what Logan and Shep and Vershik and Karov tried to do. So here I have some simulation. We saw this simulation on the first talk today. So I just sampled some random Plancherel sampled Young diagram, and then I increased its size. So here we have some pictures of growing random Young diagrams, and we already saw that there is a limit shape. So this is a repetition, but I think it's also completely clear from this picture that it seems like when your random Young diagram is starting to be very, very large, it seems like a deterministic Young diagram. And this is indeed the case. So this is a famous theorem of Vershik, Karov, and Logan and Shep. So they proved that if you look at the function, which is a profile of your random Young diagram, this function tends to a deterministic function, an explicit deterministic function, when the size of your Young diagram is tending to an infinity. And again, then what you do, you look at the fluctuations. That's a natural thing to do. And this is what Karov did. So Karov proved that you also have central limit theorem. So this means that if you look at the fluctuations around your limit shape, then the fluctuations are Gaussian. So you can see that there is a very, very appealing, it's very similar to the case of random matrices. So once you have it, you can start wondering, like, maybe there is even more. So you can ask, what is happening with the largest row? Maybe this is not a coincidence. Maybe it's really some sort of miracle that random partitions, they really give you a very good discrete analog of random matrices. And it's a miracle, but it seems that it is really a perfect discrete counterpart of random matrices. So Plancherel measure is a perfect discrete counterpart of Gaussian unitary ensembles. So all the similarities actually seems to be the same. So if you look at the largest row, the first row in your random Young diagram, the second order asymptotic is given by Tracy Widom. And once you have it, of course, it's very tempting to pose the conjecture that if you look at the law of the first k row, they must behave the same as the first k eigenvalues of GUE. So it was conjectured by Pike, Dave, Johansson, and then soon after it was proved in three different papers. So I recommend you all these papers. They're very beautiful. So we know that random Plancherel Young diagrams, they kind of, it's like a perfect discrete counterpart of Gaussian unitary ensembles. So once you have this, you can ask yourself a question. So what would be a perfect discrete counterpart of Gaussian beta ensembles? In other terms, how to incorporate one parameter deformation to this picture? So this is a very natural question, and it was suggested first by Karov and then also by Okunkov that what you should do, you should work with something which is called a Jack-Plancherel measure. So what is a Jack-Plancherel measure? So one way to think about Plancherel measure is that it comes from the following specialization. So rho is some homomorphism which is defined on the space of symmetric functions, and it is defined on generators which are power sums. So it is defined in the most simple way that it kills all the power sums except for P1. Okay? So then you just take your Schur symmetric function, you apply your homomorphism, and you take a product of these two guys, and it turns out that this is precisely a Plancherel measure.
Is this the same as the exponential specialization?
So okay, if you will take a sum over all Young diagrams, then you will get the Poissonization of Plancherel measure. But here I really fixed lambda. So also I have this d factorial factor here. But yes. So in other terms, for the experts, of course, this is like the easiest case of Okunkov Schur measures. So this is the easiest specialization when you just put P1 equal to 1 and all the other power sums are equal to 0. So okay. So you can do exactly the same with Jack polynomials. So we saw in the previous talk that Jack polynomials are some polynomials which is a one-parameter deformation of Schur. So it's a natural thing to do. You can do it. And it turns out that, in fact, you even have a very, very nice product formula for this measure. So by doing this, you actually indeed define a probability measure on the space of Young diagrams, which really looks very, very similar, but you incorporate some one-parameter deformation. So it seems that this is indeed a good counterpart to work with it. So let's try to make a simulation.
So the small j lambda alpha is just capital J lambda at all ones.
Yes, I should say yes. So this is a normalization factor, which also Hussein mentioned that Jack polynomials, when alpha is equal to 1, they're not exactly equal to Schur. They're equal up to a normalization factor. So this is a normalization. So in fact, this is somehow this identity here is in fact a formula for this factor, to be honest, because this is 1 and this is 1. But it's kind of useful to think about it this way because later we will try to generalize it. Okay. So let's try to sample random Jack Plancherel diagram. So I did it, and it doesn't look good. I mean, like this is Verschich-Kerov curve, and this is your random Young diagram. So it's not very similar.
What is alpha?
Alpha, here. Good question. Maybe 2. Maybe alpha is equal to 2. Right. And if you think a little bit about how this measure is defined, this is not a very big surprise. And this is because this measure had this property that they somehow stretch the arm length by parameter alpha, but they didn't stretch the leg length by parameter alpha. And that's exactly what you should do to correct this picture. So when you sample your large random Young diagram, you should not draw it like that. You should replace every square box by a rectangular box where the ratio between two sides is equal to alpha. So let's do this, and voila. So this is exactly like an evidence that very similarly to Gaussian beta ensembles, we have some limit shape which doesn't depend on alpha if we scale our Young diagram in an appropriate way. And it turns out to be the case. So we proved together with Valentin Ferret that there is a law of large numbers, but more importantly, the fluctuations are Gaussians, which is a much harder thing to do. So this is really a very, very nice analog to Gaussian beta ensembles. And of course, again, once you have this, it's too tempting to pose such a conjecture. So that's what you do. So we basically said that if you look at the second order asymptotic of first k rows, it must be the same as the second order asymptotic of the k largest eigenvalue of Gaussian beta ensembles. And it turns out to be true. So this is indeed a really, really good discrete counterpart of Gaussian beta ensembles. So what do you do next? Now you ask, okay, so now how can I incorporate this potential V? So we had a super large class of probability measures for particles because we had this potential V that could be pretty much anything. What you can do with random partitions? And it turned out that actually, when you're trying to somehow answer this question, it really depends where do you come from. So there is not one obvious way how to define some model that makes sense that will try to have all the nice asymptotic properties. And this is indeed what happens. So there are several different models, and all of them are different. They are also somehow coming from different worlds. So the first idea, which was due to Borodin, Gorin, and Guyonnet, is that what you do, you basically just take, I'm simplifying here things, but you just take a definition of Gaussian, of beta ensembles, and you just force your particles to live on the lattice. So that's one thing you can try to do. Then your probability space, and this is important, this is not a probability space of Young diagrams of a fixed size, like with the Plancherel measure, but it's a probability space where your parameter is the number of the rows. And what you do then, you take n tending to infinity, and then you can ask asymptotic questions. So what they proved for their model is that you have law of large numbers and central limit theorem. There is a different idea, which is coming from representation theory. So remember, I told you that Plancherel measure, if you think about it, it really comes from representation theory of the symmetric group. So what you do, you take regular representation, and you look, what is the typical irreducible component? But you can do exactly the same thing with pretty much any representation of the symmetric group. You don't have to start with regular representation. So this was an idea of Philippe Bien, who proved that if you have a sequence of representations, and if this sequence has some nice properties, namely, you control what are the characters on long cycles, how they behave asymptotically. So the first condition basically tells you that they do not grow too fast. And the second condition tells you that if you compute a character on two disjoint permutations, you want that asymptotically it will be the same as the product of two characters evaluated in these two permutations. And then Philippe Bien proved that once you have these two conditions, you have law of large numbers, and then Piotr Śniady, he generalized this condition so that you can prove central limit theorem. And we use this idea, and we basically try to extend it to the Jack case. So you also saw on the talk of Hussein that there is this very natural notion of irreducible Jack characters, that you basically just use the fact that irreducible characters of the symmetric groups are the coefficients of the Schur symmetric function. So you can just do exactly the same thing. You can define probability measures by doing this. So you start with some functions on Young diagrams. You think of them as some kind of weird alpha characters. They do not have a representation theoretical meaning, but there are some functions, and you can decompose it into irreducible Jack characters. Once this thing defines you a probability measure, it turns out that you can prove law of large numbers and central limit theorem when these conditions are satisfied. Yes?
So C mu alpha when alpha equals 1 is just the size of the cone?
Yeah, this is some normalization factor. It's slightly more complicated because you have to multiply by alpha to some appropriate power, which is related to. So I didn't want to make it too explicit, but this is just a normalization factor. Important thing is that this is an irreducible Jack character, but you have to normalize it. And this is not too important. And there's the third idea. So this is an idea that was suggested by Bordin and Olshansky in their paper on Z measures. So what they said, they basically said, like, just do the same what Okunkov did, take Schur measures, but replace Schur by Jacks. To be more precise, you take two homomorphisms from the space of symmetric functions into complex numbers, and you just want that this sum converges, and that this thing actually defines a probability measure. So if you evaluate the first homomorphism on Jack and the second homomorphism on Jack, you take a conjugate. You just want that this is always a non-negative number because you want that this will give you a probability. So this condition, and this is an important remark, this is a very non-trivial condition. I mean, it's a very interesting problem, and I do not know if anything is done to classify pairs of two homomorphisms that will actually satisfy this property. And then you sample your Young diagram proportionally to this. I mean, to be more precise, proportionally to this with the normalization factor.
So very short. How critical is that you take complex but not reals?
So this is a good question. So again, okay, maybe let me do this. So there is one trivial case when this is satisfied. And the trivial case when this is satisfied is when rho 1 is equal to rho 2. Okay? So then think that then it can be any complex, pretty much any complex specialization. Of course, such that this condition is satisfied. But this condition is just a condition about the growth. And this is like a trivial case when you can define measure like that. All the other cases are non-trivial. So I think it's a very, very interesting question to classify pairs of row 1 and row 2 such that this condition is satisfied.
But that's what he's saying. I think that if you force row 1 and row 2 to live on R, then this might be easier.
Yeah, and yes, I mean, it's not easy, but actually this is the second case where we can say something about it. This is exactly what I'm going to talk about. So, but that's why I said, like, when these two guys are just complex, completely arbitrary, try to classify it, I think it's a very difficult problem. Okay.
Can I ask that?
Yes.
In what sense is this using the Cauchy identity? Or is Cauchy identity?
So the Cauchy identity tells you that if you sum over all lambdas, product of two jacks divided by the normalization factor, this is equal to the exponential of this kernel. So if this is convergent, it means that you can sum everything and you can normalize and you have a probability measure, which now is a probability measure on all Young diagrams. So you can see in all these three models, you have probability measures that live on three different spaces. In the first one, we have a fixed number of rows. In the second one, we have a fixed size of your Young diagram. And in the third one, you have all Young diagrams. And again, so one thing that I kind of hidden here is that to state this, you actually need some parameter which is telling you, which is growing somehow, right? I mean, we are talking about asymptotics, but it will be clear soon how to incorporate such a parameter. So this is a theorem of Alex Moll that he proved that in this very special case, when also you have some kind of technical assumptions related to this growth, you have law of large numbers and central limit theorem. And moreover, for these two models, we actually proved it also in the high and low temperature limit, namely not only for alpha fixed, but we could also prove that alpha can change together with the size of your model. So this result here, I actually presented it here at IPAM 4 years ago. And then I had this question, which is a very natural question. So we have these three kind of completely different models. What can you say about, like in all these models, we are proving similar things. Can we relate them somehow? One thing which is very clear is that all these three models, they're covering the Jack-Plancherel case. More directly or less directly, but they do. So this is kind of clear, but what else? Like, what can you say about it? And then when I was presenting this result, it was a question that always people were asking. So today I will try to answer this question. And first, I will introduce a different class of this large class coming from the third idea of probability measure, where we are not looking at the specialization that Alex Moll was looking at. So row 1 is not equal to row 2. And this is exactly the case for which we know that there are many examples. And there are many examples because of this theorem of Kerov-Okunkov and Olshansky. So this is maybe a little bit complicated, so it looks too scary. The only important thing that you need to know is that there is a huge space, which is called the Thomas simplex. So it's a space of like 2 infinite sequences of reals. And for each such a sequence, I can produce some positive homomorphism, Jack positive homomorphism. So this gives me that actually there is a very, very large class of Jack measures. We call them Jack measures of Plancherel type. So what we do, the second specialization, we just take Plancherel. So this is this trivial specialization where only P1 survives. But for the first specialization, we take any specialization. And we know that there are many. So that's the point. So we know that there are many. So essentially, you can take any sequence, infinite sequence of V's. We know by this theorem that there are many sequences like that. And it defines you a probability measure on the set of all Young diagrams. So let's look at some examples, because maybe the formula is not so clear. So the first example, the easiest example, is if I take V equal to 1, 0, 0, 0, 0. So this gives me precisely Jack-Plancherel measure. And this is Poissonized Jack-Plancherel measure, because remember that this measure, it lives on the whole set of all Young diagrams. And here I have this parameter u. So the parameter u it's going to be important because it's going to tell me what is the typical size of a Young diagram that I'm working with. So there's another example. It is an example that was also studied in the literature. So it fits into z measures, which is called the Poissonized Jack-Schurweil measure. So it corresponds to the geometric to the geometric sequence. So take a geometric sequence. It turns out that actually you still have a very nice product formula. These are pretty much only 2 examples that we know that we have nice product formula. But you can see that actually there are some constraints. And these constraints are really coming from this classification. So you cannot just take any u and any c, because then you will get a signed measure. So there are some constraints that you need to take care so that your measure is really a probability measure. But still, we just need to know that u divided by c is an integer, so there's no problem to choose u and c such that such a condition is satisfied. And there are many, many other examples. These 2 are classical examples. So our first result is that we prove law of large numbers and central limit theorem for this model, so for this new model. And we do it also in high and low temperature regimes. So let's look a little bit at these assumptions. They might look slightly technical, but actually they're not that technical. So let me tell you something about this parameter u. So I told you that you need to have some kind of parameter that is telling you what is the size of your model. So if you compute an expectation of an area of your Young diagram with respect to this measure, it turns out that this is just u. So this means that u plays the same role as in the finite setup. So we want u to go to an infinity. So the first condition tells you that u is going to an infinity, and it is going fast enough. Namely, if alpha divided by u square, then in the limit it's 0. But the second condition tells you that we allow to study the regime where alpha is not fixed. So if alpha is fixed, this g will be equal to 0. But if alpha is growing together with u, then you will have something interesting. Okay? And what we proved that there is a universal shape which depends only on your sequence of v's and on your parameter g, which is telling you what is if you are in the high temperature regime or not, such that the random Young diagram, the profile of your Young diagram converges to this shape. So the convergence is in the supremum norm in probability. And we also proved central limit theorem. So this is the first result. And then the second result is that now we look at our previous theorem with Śniady, and what we proved is that the limit shape that we had in our previous theorem, it's precisely the same. So it is the same in these 2 different models. So the first model is coming from Jack measures, which is a generalization of Schur measures. The second one is coming from this idea about representation theory and characters. And it turns out that this shape is precisely the same shape. Any questions so far?
The shape is in what way is it depending on the precise choice of measure?
So that I will come to this. So in fact, the way we control this shape is via combinatorics, and this is where combinatorics appears. So it's coming. So let me just show you one more picture, and then I will show you one application also of our theorem. So this is an example of a low temperature limit, which means that g is equal to -1 divided by 4. So that means that your alpha is actually tending to 0, and it is tending to 0 with the same speed as the size of your Young diagram. So now you can see that your limit shape is drastically different. So you don't have this smooth curve anymore. You have an object which looks very discrete. And actually, if you think a little bit about the scaling, how we draw our Young diagram, this is not very surprising. Because remember that we need to keep the ratio between these 2 sides to be equal to alpha. So here, alpha is behaving like 1 divided by d. So it means that in this picture, the height of each box is actually fixed. So when you tend to infinity, the height is fixed. So it's not a big surprise that the shape will look like that. But this also means that this shape is uniquely determined by each row. So in fact, to tell you what is this shape, I would need to know what is the limit of the first row, the second row, the third row, and so on. And again, 4 years ago when I was here, I presented this result. We knew that the shape should look like that. We had absolutely no idea what is this limit. So for this precise example, when g is equal to -1 divided by 4, the first row, it seems that after appropriate scaling, it converges to this number. So I showed it here, and I said, we have absolutely no idea what are these numbers. So if anyone knows, I will be very happy to know. And yeah, we didn't know what to do about it. So one of the applications of our theorem is that actually now we know what are these numbers. So it turns out that in this high and low temperature regime, the rows are given by zeros of Bessel function. So here there is a plot of an appropriate Bessel function, which corresponds to my example here. So g is equal to -1 divided by 4. And I asked Sage to tell me what is the smallest zero, and I put it into my formula. You can see that. Maybe you cannot see it because it's very small, but it's like 3, 3, 6, 4, 9, 7, 2, the same. So this is.
You tried before that. Did you try inverse symbolic calculator?
Sorry, did we try what?
There's a thing that's called inverse symbolic calculator. You have a decimal number. You go online and then it tells you, well, maybe that's a zero of a Bessel function.
We didn't do it, and maybe it will save us a lot of time. so you know, we were generating these numbers. I was asking everybody if they saw these numbers somewhere, and no one knew. And only
that workshop in February of 2020?
Yeah.
I was there.
Okay. Anyway, now we know. So okay. So now a little bit about the method, and also this is where combinatorics appears. So first of all, how you can work with this sort of problems. So there is a very nice method which allows you to translate problems about random Young diagrams by problems about random probability measures. So it turns out that there is a correspondence between Vershik-Kerov and Logan-Shep curve and Wigner's semicircular law. So I actually didn't tell you this, that it is not only similar, the similarity is not only that we have limit shape, but actually the similarity is much stronger. So there is a correspondence between continuous Young diagrams and probability measures, and this correspondence gives you that if you look what is the corresponding measure to the Vershik-Kerov Logan-Shep, it is precisely Wigner's semicircular law. So this is something which is called Markov-Crane correspondence, and it is given by this formula. So if you want to know this, there is a formula, but for now, just the important thing is that you can somehow translate your problem by a problem about probability measures on the real line. And one thing that we proved is that our Young diagram, our limit, it is uniquely determined by the moments. So what you do, you switch to the probability measure, you compute the moments, and if you know that your measure is uniquely determined by the moments, it basically characterizes your limit shape. So the question is, what are the moments of the limiting shape? And the moments, it turns out that the moments actually have a very, very nice combinatorial interpretation. So first, let me introduce Lukasiewicz paths. So Lukasiewicz paths are lattice paths that live in the positive quadrant, such that you have up steps of arbitrary height, you have flat steps, and you have down step, but only down steps you can go only down by 1. So this is an example of a Lukasiewicz path. This is a Lukasiewicz path of length 10. And now I want to count Lukasiewicz paths, but I want to count them with some weight. So what is the weight? The weight is that for the up step of increment k, I just put a weight vk. So remember that I have this sequence of v's. My limit shape is coming from this sequence vk. So for each up step, I put vk. For the flat step, I do something funny. So I put j times g. So g is my parameter that also plays a role. When you have a fixed alpha, g is equal to 0. So this means that actually you will never see any flat steps. But when you have a high temperature regime, then g is non-zero, and you will count these flat steps with some weight. And what is j? J is the height. Okay? And finally, for the down step, you put 1. So here, the weight of this specific example is given by v2 times v1 times 1 times 1 times v3 times 4 times g, because this flat step is at the height 4. Okay? So this is the weight. And it turns out that the moments of our limiting measure are given by this very nice combinatorial formula. So what you do, you just sum over all Lukasiewicz paths of a given length, and then you sum them with respect to the weight that I just defined.
This looks very much like Flageolet's theorem for the...
Except that this weight is something new, so it's something weird, and especially the fact that that it really looks how high you are.
Yeah, and there also you only have Motzkin paths, whereas here you have Lukasiewicz.
Yeah.
So, but do you have a continued fraction generating function for it?
So this is something we didn't do, but I think it should not be maybe too hard to try to do a continued fraction. Yeah, and we didn't look. So okay, so let's maybe look at some examples. How you can, for instance, how you can see from this formula some classical results. So first example, fixed temperature, g is equal to 0, and v is equal to 1, 0, 0, 0. So what does it mean? It means that whenever you have an up step, which is not of increment 1, you put weight 0, so we don't count them. Okay? And it also means that whenever I have a flat step, I also have a 0, so I also don't count them. So this means that I'm just counting Dyck paths. So this means that the moments are given by the Dyck paths, and this is fairly known that these are just moments of semicircle law. So it is one of the very first exercise when you are working with a semicircle law to prove that semicircle law is that the moments are given by Catalan numbers. Okay. So let's now look again at the fixed temperature regime, but completely arbitrary sequence of V's. So I told you that there was this theorem of Bian who proved that the VL is something which is called the free cumulant of this probability measure. So free cumulant, and by the way, this was a very beautiful result because somehow what Philip discovered is that asymptotic representation theory of the symmetric group is somehow governed by free probability theory. And it's really, really nice. So I will not define what is a free cumulant. I mean, I will define it in a combinatorial way. So you can define free cumulants by saying that moments are given by a certain combinatorial formula in terms of free cumulants, and this is invertible. This formula is invertible. So this means that you can define free cumulants in terms of moments. So another way to think about it is that moments is some kind of measure that tells you something about your probability measure. There are other quantities that tells you something about your probability measure, and sometimes they're better. So in this case, free cumulants are better. And you can always express moments in terms of cumulants or free cumulants in terms of moments. So what is this free cumulant formula telling you? Is that it's telling you that you have to sum over all non-crossing partitions of size L, and then for each block, you take a free cumulant indexed by the size of this block. Okay? So here, for instance, I draw all the non-crossing partitions of size 4. So in fact, I draw all the partitions, and there's only one which is crossing, so we don't count this. And then for each block, we just put R indexed by the size of this block. Okay? And you sum over all non-crossing partitions. So this is a formula that tells you that the moment can be expressed in terms of free cumulants. So, but now I claim that there is a bijection between non-crossing partitions and Lukasiewicz paths. And this is a very, very classical bijection. It's very easy. And it's also very nice because it turns out that it sends sizes of the blocks into up steps. And it preserves sizes. So how does it work? What you do, you just somehow take the first leg of your partition. You look what is the size of this block. It's 3. And then you draw an up step of the size of the block minus 1. So this means 2 in this case. Now I go further. I see a new block. This block is of size 1. So I draw an up step of increment 0, because it's always minus 1. And then I see a leg that I already saw, that in a block which I already saw. So if there is a leg in a block which I already explored, I'm going down. And I continue. There is a new block. This block is of size 2, so I go up by 1. Then there is a new block of size 1, so I have a flat step, and so on. Okay? So this is a bijection, and this bijection has this property that the increment of up steps, it is precisely the size of the block minus 1. So this means that this moment-free cumulance formula is actually ML is equal to the sum over the weights that I just defined, with one thing, that R1 is equal to 0. But for random partitions, this is always the case, because R1 corresponds to the flat steps, and the flat step has weight 0. So in other terms, what I just said is that we just recovered a theorem of Bian combinatorially for the fixed alpha, for the fixed temperature. And VL is some new one-parameter deformation of the free cumulant, because we can see that VL, if G is equal to 0, this is precisely a free cumulant, but if G is non-zero, it's some like G deformation of free cumulant. So you can also ask all sort of your favorite probabilistic question about these new cumulants that we are planning to explore in the future.
So flat step is corresponding to single part blocks.
That's right. That's correct.
And what is the new statistic on those blocks? Like you want to have level. Is it like nesting level or?
So that's why we are actually using these Lukasiewicz paths, because it is much more straightforward. But of course, you can try to understand what is this height, and this is related to some nesting, but it's somehow less direct on the picture of non-crossing partitions. But yeah, you can try to put weights there. So let me just finish with a riddle for you. So there is some kind of combinatorics that we don't understand here. So we have a formula for the moments. It's a combinatorial formula where you sum over these Lukasiewicz paths. But there's also theorem of Śniady, who also found the combinatorial formula for V's in terms of free cumulants. And this combinatorial formula is very different. It involves maps, so it involves things that were presented in the previous talk. So what you do, you sum over all rooted bipartite-oriented maps with L edges, and with some colorings of black vertices, where there is this very funny condition that the coloring has this kind of property that whenever you look at any non-trivial subset of black vertices, the number of white neighbors has to be smaller, strictly smaller than the sum of the colors. So I have an example for you. So I draw all the orientable maps with 3 edges. And then you can actually see that for these 3 examples, it's impossible to color it with this rule. So this means that they will not appear in the formula, but all the others will appear in the formula. So this means that V3 is equal to this quantity. And the question, the riddle for you is how to prove, like if you have this, how to prove this, or if you have this, how to prove this. I mean, we have absolutely no idea. We have 2 combinatorial identities that are equivalent, and we cannot combinatorially prove that they're equivalent. So if you can prove it, please let me know, because then maybe we can prove something more interesting. But this is already very interesting for me. So thank you very much.